In this video, we're going to be talking about significant figures and scientific notation. Don't know what those are? Well, you're in luck because we're going to learn about it today. So let's talk about significant figures. So in science, measurement should only have 1 degree of uncertainty, meaning only one estimated digit, one digit that we aren't certain of. So significant figures are the certain digits and that one estimated digit. The number of significant figures will tell us the exactness of the measurement. Exactness is also called accuracy, how close the measurement value is to being the actual value measured. So essentially, significant figures allow us to report our numbers accurately. We aren't being more specific than we can be, but we also aren't being less specific than we can be. So there are 5 rules for significant figures that you need to know. The first rule is that all digits 1 through 9 are significant. So if you see a number, 1, 2, 3, 4, 5, 6, 7, 8, 9, it is automatically a significant figure. Now zeros are where things get tricky, and our remaining 4 rules are all going to be about zeros. So zeros between significant digits are always significant. So for example, in the number 2007, that has 4 sig figs, because those zeros are in between 2 non-zero numbers. On the other hand, trailing zeros, these are probably the ones that are some of the most difficult for students. Trailing zeros are only significant if the number contains a decimal point. So let's say we have 100.0. That number has 4 sig figs because those trailing zeros, those zeros at the end, have a decimal point. On the other hand, the number 100 only has 1 significant figure, the 1, because there's no decimal point, so those trailing zeros don't count. Zeros in the beginning of the number that only serve as placeholders are not significant. So anytime you see zeros at the beginning of a number, they are not significant. So this number right here, 0.0025, has only 2 significant figures. And our last rule is where things get a little tricky. So zeros following a decimal significant figure are also significant. So in the beginning, if we have a decimal point or not, those zeros don't matter. At the end of a number, zeros only count if there is a decimal point in the front. And that is true for both rules 3 and 5. Now, I personally just kind of have these rules memorized. I go through them in my head. This is how I know how to do sig figs. However, there's another way that I also like to teach sig figs that helps a lot of students. I call it the cheat sheet version, and I also call it the Atlantic Pacific rule. And it helps you determine whether numbers are significant or not by imagining the United States. So you know what the United States looks like. If a decimal is present, starts with a P, you are going to start on the Pacific Ocean side of the country. And you are going to move your way towards the middle of the country until you hit your first non-zero number, as in 1, 2, 3, 4, 5, 6, 7, 8, 9. Once you hit that first non-zero number, every number after that becomes significant. Now, if the decimal is absent, starts with the letter A, you are going to start with the Atlantic side of the country, also starts with the letter A, and you're going to do the same thing. You're going to move towards the middle of the country, and when you hit your first non-zero number, every number after that becomes a significant figure. So let's kind of take a look at what I mean. So here's our United States. We have our Pacific Ocean over here. We have our Atlantic Ocean over here. So let's say that we are looking at the number 1250. 1,250. Now there is no decimal point, so we are starting on the Atlantic side of things. And we are going to move our way towards the center of the country until we hit our first non-zero number. So we move past that 0, but then our first non-zero number is our 5, and everything past that 5 is also significant, meaning this number would have 3 significant figures in it. Now, on the other hand, let's say that we have the number 1370.00. On this one, our decimal point is present, so we start on the Pacific side and we count going this way. The first non-zero number I hit is right at the beginning, that 1. So everything after that counts as a significant figure, meaning this number has 6 significant figures in it. Let's do one more using our cheat sheet way, because a lot of students find this helpful. Let's say we have the number 0.0048. Our decimal point is still present, so we start on our Pacific side, and we count moving towards the middle of the country until we hit that first non-zero number. So we ignore all of those zeros at the beginning and just count from there, meaning this number has 2 significant figures. And that's how the Atlanta Pacific method works. If you would rather do the rules, that's what I personally do, but if you like Atlanta Pacific better, that works as well. So let's do a learning check. Which answer contains 3 significant figures? So let's look at each of these. In A, we know that zeros in the front don't count, but everything after that decimal is going to, so that number has 4. So not A. Once again, zeros in the beginning don't count, but everything at the end does, so this has 3. So B is a good answer. But you know Miss Hinkson is a big fan of select all that applies, so it's always a good idea to check your other answers. So this one, all our non-zero numbers count, but zeros at the end only count if there's a decimal, which there's not, so that means that 0 at the end doesn't count either, meaning this one also has 3. Number 2 asks us for all the zeros are significant. So when it comes to A, we can clearly see that our zeros in the front don't count, but we know zeros in the middle do, but since we crossed out those zeros, we know it's not A. Now, this time we have a decimal present, and zeros at the end count when there is a decimal present, so that means that B also works. But let's check one more answer. This time we have a 0 sandwiched and a 0 at the end. We know those count as well, so that means C is also a correct answer. Now, sometimes you can also be asked to round numbers to a certain number of significant figures. So let's say that we have the number 534,675. We can only have 3 significant figures, so we go 1, 2, 3, and then you peek next door and ask yourself if that number is going to round up. Now you know that 6 does round up a number in front of it, so that means 4 is going to round up to 5, but we just can't get rid of these numbers. They get converted to zeros. So A is wrong because it got rid of all of those numbers at the end. B is our correct answer because it kept the number with those zeros. Now, C is also correct, and we are going to get to why in just a second. So now that I've got your curiosity piqued, we'll get to that in just a minute. Let's do another learning check question, though. In which set of And which sets do both numbers contain the same number of significant figures? So in A, since we have decimals in both of them, those zeros count. So this is 3 and 4. We know those aren't the same number, so that's not what we're looking for. In B, we have a decimal again, so all those zeros count. So that means that's a 4, but this one has no decimal, that 0 doesn't count, so that's a 1. We know those aren't the same. Now in this one, remember zeros at the beginning don't count. It's only our numbers after that first non-zero number. So this has 2. But similarly, zeros at the end don't count unless we have a decimal. So only our non-zero numbers count in this one. So this is also 2, giving us our correct answer of C. Now I hope you understood why those were the answers, but if you didn't, these are great questions for you to bring to class tomorrow to ask me to go over them again. Now I want you to pause this video for a second and try these on your own. You're going to state the number of significant figures in each of the following. This is great practice for you, so pause this video and come back when you're done. All right. In question number 5, you should have gotten that this number only has 2 significant figures. The zeros in the front do not count, but the 0 at the end does, as does the non-zero numbers. Number 6, you should have gotten 4. Because of that decimal there, everything counts. For number 7, this number only had 1 because remember, zeros in the front don't count. 8 had 3 significant figures in it. Because of that decimal, everything counted. Now 9 may have tricked you up, and the important thing about 9 is the unit, B's. Numbers that are exact counts are all significant. If I say that I have 32 students in my class, I have exactly 32 students in my class. There's not a chance that I actually have 31.6 students in my class or that I actually have 32.3. I have 32 students. So B's is an exact count. Therefore, all of these numbers are significant. So that one has 7. I bet that tricked you, and that's okay. So always check the unit before doing sig figs because exact counts, all the numbers are significant. Now the reason we need to know about significant figures is you are going to be using them in calculations. So a calculated answer cannot be more precise than the measuring tool. Your calculator is perfectly happy to give you a string of 10 numbers, but that doesn't mean that that is actually accurate. So a calculated answer must match the least precise measurement. So we can only be as sure as our least good measurement. So significant figures are needed for final answers from adding or subtracting or multiplying and dividing. So if you are having to do some sort of math, significant figures come into play. So let's talk about adding and subtracting. So the answer has the same number of decimal places as the measurement with the fewest decimal places. So if we have the number 25.2, that has 1 decimal place. If I'm going to add the number 1.34, which has 2 decimal places, if I punch that into my calculator, it's going to tell me 26.54. But that doesn't follow the rules of significant figures. A correct answer would be 26.5 because my least certain answer only had 1 decimal place on it. That makes sense? So based on that, why don't you pause this video and answer these questions on your own. Let's see how you did. For number 1, your calculator would have told you that you had 256.75. But we have 2 numbers that only have 1 decimal place on them, so our answer can only have 1 decimal place, so we would write down 256.8. For number 2, your calculator would have told you 40.725, but once again, we have a number that only has 1 decimal place, so the answer 40.7 would be correct. Now, multiplying and dividing is what we are going to do the most of in chemistry, so make sure you pay special attention to this as you're going to be using it a lot. So you're going to round or add zeros to the calculated answer until you have the same number of significant figures as the measurement with the fewest significant figures. So you're going to look at your numbers that you're using, and whichever one has the fewest significant figures, we're not talking decimal places anymore, just significant figures, that's how many significant figures your answer can have. So for example, if I take 15.7 and multiply it by 0.63, I am taking 3 sig figs and multiplying it by 2 sig figs, which means I need to round my answer to 2 sig figs. So let's do some practice problems together. Pause this video and come back when you have your answers rounded to the correct number of sig figs. All right, let's see how you did. When you multiplied 2.19 times 4.2, your calculator told you 9.198. But since this second number here only has 2 significant figures, our answer can only have 2 significant figures, making 9.2 correct. Now, if you took 4.311 and divided it by 0.07, your calculator would have given you this great long number. But this number right here only has 1 sig fig, which means our answer can only have 1 sig fig. So we had to round it down to 60. Now, number 3 had a lot of numbers in it. And when you entered into your calculator, it gave you another big answer back. But this number, right, we had 2 numbers in here that only had 2 sig figs. This one right here and this one right here. So that meant our answer can only have 2 sig figs, so we would have rounded our answer to 11. Hopefully you got the hang of this. If not, this is a great question to bring to class tomorrow. Now, the last thing we need to talk about is scientific notation. So what is it? Scientific notation is a way of expressing really big or really small numbers. It is best used for very large and very small numbers because it is more concise, meaning it makes things smaller. So scientific notation consists of 2 parts: a number that's going to be between 1 and 10, and a power of 10. So it's always going to be in the formula of n, which is a number, anything 1 through 10, including decimal places, times 10 to the certain power. Please keep in mind when you divide a number by scientific notation, you want to put the scientific notation in parentheses, or else your calculator is going to do weird things on you. So, if you were given a number in standard form and asked to convert it to scientific notation, you place the decimal point so that it is 1 non-zero digit to the left. There is 1 non-zero digit to the left of the decimal point. Then you are going to count the numbers of decimal places the decimal point has moved from the original number. This will be the number of places you move is the exponent on the 10. If the original number was less than 1, the exponent is going to be negative. If the original number was greater than 1, the exponent is going to be positive. So let's look at some examples. You are given the number, this number. It's a big number, so we want to put it in scientific notation. So the first thing we're going to do is move our decimal. Remember, all numbers actually have an imaginary decimal point at the end of them if there's not one there. And we are going to move that decimal all the way to so there's 1 non-zero number in front of it, the 2. And we move that decimal 1, 2, 3, 4, 5, 6, 7, 8 places. So that means our scientific notation is going to be 2.898 times 10 to the 8th. The exponent helps us get rid of all those extra zeros. Let's try another one. This time you're given this very small number. Once again, we are going to move our decimal so that there is 1 non-zero number in front of it. So we move it 1, 2, 3, 4 spots to put a decimal there. So we make our number 5.67, and it has moved 4 places. So since it started out as a number that was less than 1, it's going to have a negative exponent, so we make it 5.67 times 10 to the negative 4th. Hope that makes sense. Now, sometimes you might be given a number in scientific notation and you want to change it back to standard form. So you're simply going to move the decimal point to the right for a positive exponent of 10. Whatever that exponent is, you're going to move the decimal to the right that many places. You're going to move the decimal to the left if the exponent is negative, but you're still going to move it that many places. You may have to use zeros to fill in places. Sometimes you'll run out of numbers to move that decimal through, in which case you keep moving the decimal but keep adding zeros every time you move it. Let's look at an example. You are given the number 5.093 times 10 to the 6th. So I need to move that decimal 6 places, and since it's positive, I need to move it 6 places to the right. So I go 1, 2, 3. Now I've ran out of places, so I keep moving 4, 5, 6, and I replace those empty places with zeros, giving me my answer of 5,093,000. Let's look at another one. This time I was given this number and I see that my exponent is negative. So that tells me that I'm moving my decimal to the left. So I move it 1, and then I've ran out of spaces, but I keep going. 2, 3, 4, and I'm going to plug zeros into those extra places, giving me 0.0001976, where I moved it 4 places to the left. Hopefully that makes sense. Now I want you to pause this video and try these on your own. You are going to take these numbers and express them in scientific notation. Come back when you're ready to see your answers. Let's see how you did. Here are our answers. 1, we would have kept all of our numbers, but put a times 10 to the 5th at the end. That probably wasn't the best one to put in scientific notation in the real world. However, number 2, we did get rid of those zeros up at the front and make it 3.872 times 10 to the negative 3rd. 3 was another example of one that's great to write in scientific notation because we got rid of all of those zeros to just make it 3 times 10 to the 9th. 4 was also not a very good one to put in scientific notation because it just became 2 times 10 to the 0, telling us you don't move the decimal at all, but that actually made it longer. 5 also wasn't a great one to put in scientific notation, but it's always great to practice, where we moved that decimal over 1 place, meaning it became times 10 to the negative 1. How'd you do? I hope you did great. Now there's one more thing I want to talk about, and that's that you can do math with scientific notation. So you could be asked to multiply 2 scientific notation numbers against each other. If you do that, make sure you're using parentheses around those numbers, and I recommend you try pressing this into your calculator now so you can see if you're doing this correctly, because you should get the answer 1.64 times 10 to the 5th. This did take sig figs into account. Since I was multiplying, I used my number that only had 3 sig figs in it to determine how many my answer could have. So check this in your own calculator and make sure you can get this answer. Division works the same way. I could have divided these 2 numbers. Once again, please try entering these in your own calculator to make sure that you can do this. And this time, we would have gotten 5.11 times 10 to the 11th. Still only have 2 sig figs in our answer. The 10 to the number do not count towards our sig figs. Only the number in the front does. All right, that's all I've got for you. Now, make sure to go answer those questions.